Hi everyone, it's my great pleasure to present our paper on understanding Android VoIP security, a system-level vulnerability assessment. I'm Daoyuan, a research assistant professor from Chinese University of Hong Kong. This is a joint work with En He from Oppo and Professor Robert Deng from Singapore Management University. First, what's VoIP or VoIP? It stands for Voice over IP, which uses the IP network to route voice data. Compared with the traditional PSTN calling service, VoIP has a number of advantages, mainly the improved quality of service, high fidelity codecs, and lower monetary cost. Because of these advantages, VoIP is being actively deployed in modern networks and smartphones, such as the latest VoLTE and VO Wi-Fi schemes. There are some existing works on Android VoIP securities. However, they focused either on the weakness of VoIP network infrastructure or on the privacy concern of third-party VoIP applications. For the research of VoIP network infrastructure, there are two CCS papers before discovered multiple vulnerabilities in VoLTE's control and data plane function. Another paper published in CNS 2018 uncovered 4 vulnerabilities in operational Wi-Fi calling service. On the other hand, for the research of third-party VoIP applications, they mainly focus on the security issues, such as whether the traffic of those VoIP applications are encrypted or not. Therefore, it is still unclear whether Android's VoIP integration at the operating system level are secure or not. In this paper, we conduct the first study to systematically analyze Android VoIP security at the system level. Our study begins with a demystification of Android VoIP. We found that Android VoIP mainly uses the session initiation protocol, the so-called SIP protocol. This figure illustrates a typical network infrastructure of SIP, where SIP is used to initialize and establish VoIP connections. During the SIP negotiation, another protocol called SDP, session description protocol, is used to describe SIP packet contents. The actual voice data is transmitted by another protocol called RTP, the real transmission protocol. By studying Android's source code, we are able to depict the implementation of VoIP stack in Android, as shown in this figure. So first, for the SIP protocol, it is implemented by NIST SIP library, which is developed by National Institute of Science and Technology from US, and we can access these protocols through some Java packages. The SDP protocol is also implemented by the NIST SIP library, while for the RTP protocol, it is implemented in a native library called librtp gni.so file. Android provides only a handful of codecs, and supporting these codecs relying on a library called libstate-bright. Lastly, for the user agent, they are mainly implemented in 2 system applications. One is telephone application, another is the dialogue application. After understanding Android's VoIP integration, we now study all 4 potential Android VoIP attack surveys, as shown in this figure. Firstly, attacker can access a victim device physically to misset some VoIP configuration. Secondly, since VoIP applications are system-level applications, they can access permission-protected resources and also system interface in telephone manager and radio interface layer. So an on-device malicious application can attack these VoIP applications through IPC communications to obtain those VoIP-related privileges. Thirdly, a network-side adversary can send crafted payload in SIP, SDP, or RTP packets to exploit Android VoIP components remotely, causing some remote denial of service or code execution. Lastly, the popular hands-free Bluetooth device also brings a new attack surface. The malicious payload in VoIP traffic may reach to the system Bluetooth components, which can cause a nearby attack. After understanding Android's VoIP integration and its attack surface, we propose a novel approach to systematically access Android VoIP's vulnerabilities. We still use the previous figure to illustrate the basic idea of our approach. In this approach, we first automatically test Android VoIP components through on-device intent API fuzzing and network-side package fuzzing, and further combine them with targeted code auditing. In this talk, I will focus on the first two parts, and you can refer to our paper for the details of targeted code auditing. For the on-device fuzzing, we perform not only the conventional intent fuzzing, but also the system API fuzzing based on Java reflection. We first develop an on-device fuzzing framework based on the Dresser tool, which consists of a Dresser agent on the Android phone and a Dresser console on the PC. In the intent fuzzing, our target is the system VoIP application. We identify the exported components in these VoIP applications by analyzing component information in the Android manifest file, and we further manipulate intent parameters by trying both empty parameters and the parameters that satisfy a component scheme. In the system API fuzzing, our target is the unprotected system service interface. We identify them by using Java reflection to invoke Android Service Manager's list service function, which can list not only all the available system service interface, but also their accepted parameter types. We can then launch targeted fuzzing against this exposed service interface according to their parameter types. For the network side fuzzing, we first build a novel test bed, as shown in this figure, where the victim is an Android phone, and we use MJ-SIP tool to mimic the adversary. We further set up a SIP proxy server to connect all these parties into the same Wi-Fi network. Note that MJ-SIP is a command line-based SIP user agent implementation with flexible options. Here we leverage these major options, and we launch three types of remote fuzzing: SIP fuzzing, SDP fuzzing, and RTP fuzzing. Firstly, for the SIP fuzzing, we mainly use the display name and the user parameters. We will set up long user SIP name and the display name to try crash VoIP applications. Secondly, for the SDP fuzzing, we need to specify multimedia configuration file. Here shows the media descriptors we can manipulate, mainly the media parameter and the media specification parameter. Lastly, for the RTP fuzzing, we also need to generate different formats of audio files. So we will first generate a seed audio files, then we use this command to manipulate the seed audio file into different audio files. Besides this kind of direct fuzzing that generates new VoIP traffic, we further launch man-in-the-middle fuzzing that can leverage existing VoIP traffic. Now let's talk about some results. So we perform periodical fuzzing over a period of around 2 years on the recent Android OS from Android 7 to Android 9. Totally, we identify 9 vulnerabilities. 8 of them are system-level vulnerabilities, and 6 of them could be attacked remotely. And the security consequences are generally serious. We found that 6 of them are rated by Google security team as high or critical level. For the detailed security consequence, we found that these vulnerabilities can cause remote code execution, denial of service, and caller ID spoofing. Now let's go through the detailed vulnerability results. First, on the vulnerabilities discovered through on-device fuzzing, the first vulnerability V1 is on maliciously triggering a VoIP call in the VK application, which is a popular VoIP application. Because our intent fuzzing didn't identify any vulnerabilities in the system application, so we use a third-party application to demonstrate the effectiveness of our methodology. In these vulnerabilities, our attack app with zero permission can send a malicious intent to trigger VK application to launch a VoIP call. The second vulnerability is about unauthorized call transfer in the system IMS interface. In these vulnerabilities, there are 2 exposed APIs, send call transfer request API and set call forward timer APIs. They can be misused by an attacker app with zero permission to set up the call transfer. For the vulnerability discovered by network-side fuzzing, we first show the V3 and V4 vulnerability. In V3, we can see that the adversary intentionally set up a very long SIP username. In this case, the victim user have no way to reject or accept such call, therefore cause undeniable VoIP call spam due to long SIP name. And to launch such attack, the adversary can simply use this kind of command. In the fourth vulnerabilities, the attacker can crash the remote VoIP application just after user accepting a VoIP call. And the problem here is because the SDP protocol didn't have some suitable codecs or have some argument exceptions. Besides the direct VoIP remote vulnerabilities, we also identified 2 vulnerabilities that could launch from nearby Bluetooth device. This figure illustrates the connection between a hands-free Bluetooth device and the system telephone applications, because they use AT and CRCC command to transmit the data, and the SIP phone number will be also used as a number highlighted here. However, the system component didn't expect a very long SIP name. Therefore, in the vulnerability V5, remote code execution could be caused due to an stack buffer overflow that exists 500 bytes. The vulnerability V6 is similar, but this time the problem is an integer underflow. And you can refer to our paper for the detailed vulnerability code in V5 and V6. Lastly, we also discovered 3 vulnerabilities through code auditing. First, in the vulnerability V7, the attacker can misuse the SIP profile name format by set some path transfer here. In these vulnerabilities, the attacker can either cause the private VoIP profile dump to the SD card or simply cause a permanent denial of service by overwrite that SIP profile. In vulnerability V8, the attack misuse a special number. So this special number, say after 911, it will be transmitted as the normal 911 number by the vulnerable VoIP applications. In the vulnerability V9, the root cause is also a special symbol called phone context, which is originally used to set up the prefix of a phone number. For example, phone context +1 will be equal to +1 and the phone number. So in this case, we can mimic Google's phone number and therefore cause the caller ID spoofing. We further try to understand the root cause of those vulnerabilities. We found that 3 of them are previously known. However, we also identify a new vulnerability causes, which is called incompatible processing between VoIP and PSTN cores. As shown in these tables, the incompatible behaviors could be the phone number length, where SIP can have arbitrary SIP name length, while in the traditional PSTN, the number should be smaller than 513. And in the SIP, furthermore, in the SIP URI, there are no special characters. However, in the PSTN, those special characters have special meaning. So this causes some incompatible behavior. To summarize my talk, we first give the first demystification of Android's VoIP integration and all its 4 attack surveys. Then we propose a novel approach that assembles on-device intent API fuzzing, network-side packet fuzzing, and targeted code auditing. Lastly, we present new and comprehensive vulnerability assessment results, which is the major contribution of this talk. Okay, thanks for your attention. That's the end of my presentation. Please feel free to email me if you have any questions.